So I introduced yesterday Karman-Howard equation and also defined this length scale called Taylor microscale, which was related to the behavior at the origin of this function f of r. So we fitted a lowest order fit to that, which was a parabola. And if you remember, I defined f double prime, that is the derivative of the function, second derivative of the function at r equal to 0. This has the dimension 1 over length squared because f is up prime over up squared. So when the 2 points are the same, then up squared or up squared just gives you 1. So it's a non-dimensional quantity, and f double prime has a dimension 1 over length squared, and it's also negative. So we just put this as 1 over lambda squared, and that was how we defined it. So f is now f0, which is 1, minus r squared over 2 lambda squared. This is f of r, this parabolic fit. So when r is 0, that is where f is 0, that is you bring it down all the way to this axis, you have the situation r equals square root 2 lambda, and that's square root 2 lambda. Okay. So that's how I defined the length scale lambda, and in fact one experimental way of determining this lambda is to compute this function, get its curvature, and you have lambda. Usually it is very hard to get the curvature right, so this is not the most preferred way of calculating lambda. Another way, I also mentioned this to you yesterday, if we consider the behavior of the Karman-Howard equation near r equal to 0, that is, we expanded this and we said k, the function k, which I didn't tell you how to do, is 0 because you are collecting only terms to the lowest order in r. So I showed you this also, d by dt of 3/2 u squared is 15 u squared over lambda squared. That I wrote down yesterday. Okay. But it turns out in isotropic turbulence, which is a somewhat of a lengthy calculation to do, but you can probably see how it is done. You remember that when I wrote down the whole equation, I had a dispersion term, which was nu dui dxj, and things like that. Say duk dxj. If I wrote down an equation for rik, things like that. So you expand it, they contract all these terms, all these indices, and then you use the isotropic relation. The isotropic relations usually, it means that, so I have, let's say, u in the direction x, then you take the derivative du dx and square it. It is the same thing as taking v in the direction y, for instance, right? So dv dy squared, this is equal because of isotropy. There is no difference between the operation you perform on u with respect to x in comparison with the operation you perform on v with respect to y. And similarly, W with respect to Z, etc. So you use all those things. The dissipation, that is the rate of change of energy, turns out to be 15 nu du dx squared. So this is something, last night I tried very hard to give you get you a small, brief proof, but it took a lot longer, I mean 4 or 5 pages, so I don't think I want to do it. But that is the standard relation. So basically what it means is if you measure the gradient of velocity in one direction and square it, average it, and multiply by nu, you will get the dissipation. So just equating these two, you have to take this on faith, okay? I can give you the reference to the paper in which it was first computed by G.I. Taylor, 1935. I have the paper on my phone. I can send it to you if you want. But it's sort of somewhat elaborate. I tried to do it more simply last night, but it was also complicated enough. So lambda, therefore, has the definition also u squared over du dx squared. So that's the definition. This is an easier thing to do. You measure the mean square velocity, take the gradient squared, and average it, and you have the relation. So, but this is not the only length scale with which we are concerned most of the time. For example, f of r here, it sort of goes down like that. Remember what that is. It's just that. If the velocity here and the velocity here are correlated, you will have a finite value of f, right? It's just the cross correlation between them that gives you the finite value. So you might say that this length here, over which f of r vanishes, is another length. It's a length over which things are correlated in space, you might say. However, as you know, this function goes down, as you might imagine, this function goes down to 0 in a very smooth way, and this distance is not a very easy thing to define. So one instead defines a much more specific thing, which is integral 0 to infinity of f of r dr, and you call this, say, LP. Okay, so it's simply not taking this somewhat dubious length over which it is correlated, but it will simply tell you, for example, it will, the area there, well, something like that, and I don't want to use the same lambda here. So, you know, this area is the same as this area, then you have this LP here. LP is typically larger than lambda, except when the Reynolds number is very small, then it's almost the same, more or less. You can also define another length scale from G. G of R is, if you remember, un or un squared. Un meaning instead of taking velocities like that, that's what f is, and this one is simply normal to the separation line r here. So this is un, that's un. So this you can do this as well. So 0 to infinity of g of r dr, and g of r is simply f of r plus 1/2 r f prime dr, and this will give you LP by 2. Now these length scales are important because this is what allows you to define the Reynolds number in a flow. So you have a box, big box you have just shaken and left on the desk, what is the length scale in the problem? It's not the size of the box because it is technically infinitely large. That's how you have strict homogeneity. In practice, of course, if the box is finite, you just leave out the things around the edges and then the rest of it you consider. But technically, that's not the length scale of the flow. The flow has some uh, activity inside with some length scale which may be related to one of these. And that's the reason we define length scales. So now you are at liberty to define the Reynolds number of the flow. Say RE, just say RL P if you like. This is U prime. U prime now, here, let me put it this way. LP by nu. So you have a fluctuating velocity and its mean is 0, so you cannot use the mean value as the characteristic velocity, but you take the next immediate moment of it, which is the mean square, and take square root of it. This is the so-called RMS velocity. People just say that root mean square velocity. So that's one Reynolds number you can define. Likewise, you can define, of course, RLG is just half of that, so I don't have to write it separately. But R lambda, RE lambda, let's say, this one here, you define the same way using lambda instead of LP. And so this is the so-called integral scale Reynolds number. Integral scale Reynolds number. Integral scale because LP is just obtained by integrating this function f. And this is the microscale Reynolds number. So if you look at any paper on turbulence, you will either get this Reynolds number or RLG, or you get this Reynolds number. So you have to know what Reynolds number one is talking about. Usually they specify this microscale Reynolds number. Sometimes they say Taylor microscale, but basically it is the same with or without the suffix Taylor. And the integral scale is always defined that way. Now, how are these two Reynolds numbers related to each other? That is also something we should have some idea about. And you can do this by using one of the properties of turbulence that I mentioned maybe the day before yesterday. That is, as you change the Reynolds number, say R E lambda, and you plot energy dissipation, that is this quantity here, from now on, please excuse me that I will use epsilon for this quantity, that is energy dissipation. It is simply because everybody else uses it, and if you open any paper, you will see epsilon as the symbol for this quantity, so I might as well use it. So epsilon, in some non-dimensional way, you don't approve of what I'm doing? What's that? Yeah. Yeah.
And then in air.
Yeah.
How would be the Reynolds number different depend on the system I've created in turbulence in or?
Yeah. So if I understand your question, you have one fluid in one box, another fluid in another box. I shake them, both boxes, the same way, and you want to know whether the flow is the same?
Yeah, because we in these expressions, it's really what determines LP or lambda.
Yeah. Give me another half hour, and if you don't get the answer, let me know, okay? Now, the thing, of course, is in some respects they will be the same. In some respects they will not be the same. and I want to tell you what respects they are the same, and you will see. You will see shortly. But it is a good question, so I'll try to answer it. So now plot the energy dissipation in a given system now, in a given box with a given fluid, etc. And you shake it and see how fast the energy is being dissipated. Now, this is a non-dimensional quantity. You want to non-dimensionalize this somehow or the other. And what is the right way to normalize? Let's think for a minute. Suppose I have a tank like this, and I have a propeller which is creating turbulence. It's just spinning at some velocity u, and it creates turbulence at some length scale, which may be related to this in this case. So like that. And so it's pumping in energy at the rate uq by L, because dimensionally that's the power. It's a rate, U squared is the kinetic energy, L by U square, L by U is the time. So it's just the rate at which energy is being pumped in. Now, for this to be stationary, that is to say things are not changing with time, it's clear that the energy has to be taken out at the same rate, right? So how it happens is by viscous action and the small scales that are created, but it has to happen like that. Therefore, epsilon, that is the energy dissipation, is scaling always on a large scale velocity and a large scale length. So what I am going to do is plot this epsilon LP over U prime. So to make it simple, let's call this this root mean square velocity as U prime from now on. And so I just say U prime cube. So that's the way to normalize. And I was telling you the other day, less specifically than this, this sort of comes down, and then beyond a certain Reynolds number, RE lambda, let's say 50 to 100, something like that. In that range, and beyond that, it sort of flattens out. And let's call this a constant as A. So A, this is of order 1. And exactly what it is depends upon what sort of flow it is, that number. This is, by the way, a totally empirical observation, but a very important observation. There is no theoretical model that gives you this. However, I refereed recently a paper by an author who claims he has some mathematical underpinning, which I actually gave a positive report on the paper. So, but I won't talk about it much. The point is, when the Reynolds number goes to infinity, you can interpret that as viscosity going to 0. So I mentioned this yesterday, but I repeat it. So even when viscosity is going to 0 or becoming very, very small, turbulence is dissipating energy the same way. So that's extraordinary in a way. That, I think, is one of the defining characteristics of turbulence, that it's finite dissipator even in the limit of vanishing viscosity. Now, but you shouldn't be sort of blinded by this observation. If you take a flow near the wall in a channel, for instance, epsilon is not of order unity, it's of order Reynolds number. I mean, it's a very high dissipator. So what happens there is, if the Reynolds number is, say, 1,000, 1,000-fold energy is being dissipated than normally would happen in a flow like this. But 1,000-fold, 1,001-fold energy is being produced as well. In other words, what maintains a flow is a small difference between two very large quantities there. it's not clear to me why turbulence does that. I mean, why does it need to produce so much and dissipate so much and then only a little bit of the balance to maintain it? That's not clear. But basically, in this case, that kind of question doesn't arise. But remember that something like this is nearly always true as long as you are far away from the walls. This observation holds. So we can say that epsilon LP over U prime cube is a constant like that. Then you can relate the two of them. And how do we relate the two? For epsilon, we put 15 nu U prime squared over lambda squared. That is LP over U prime cube. This is A. So I have here, let's say U prime squared here. So there's one U prime that goes with that. And I have, say, nu squared here and nu here. You have to manipulate a little bit. Basically, you have RE lambda squared is, so I get it right, 15 divided by A times RE of LP. So the microscale Reynolds number, aside from this factor sitting in front, is like the square root of the big Reynolds number. Okay. So when people say Taylor microscale Reynolds number is 100, the big Reynolds number is roughly, 15 times the square of that. No, I mean the square of that divided by 15. So you can calculate those things. Okay, so normally people will say simulations done at Taylor microscale Reynolds number 100 or something like that. But that's what they mean. Okay. This, by the way, I think 1984 was the first time it was all done properly. And thereafter, simulations have actually shown, they have extended it even further. The main point I wanted to make is that in simulations, this constant of order unity depends upon how you force the flow. So in some ways, it is not exactly the same constant in all simulations and in all flows, but in any given simulation, it is flattening out to a constant, which may be slightly different from the one in another flow. But a typical number would be something like 0.45, like that. Okay, so that's one aspect of it. Now, let's look at, we are now getting to the point of being able to say something about Kolmogor's hypothesis and all that. This KH equation is in real space, right? It's all related to correlation functions measured in real space. You can take the Fourier transform of that. Sometimes it is useful to look at in the Fourier space. And although most of it was obvious yesterday, but I write the equation and tell you what is. So d by dt of E of k, you remember this is the analog of f. F is the one scalar function of a scalar variable in isotropic flow. That's the only thing that matters. In spectral space, a corresponding thing is this, which is the energy contained in spherical shell of size dk around k. So this here is has two terms in it. One is the dissipation term, which is 2 nu k squared E of k. You remember how this k squared comes from. It comes from the fact that you have a second derivative in space and each derivative in space gives an ik in the Fourier transform, and I squared k is minus I squared k squared is minus k squared. So, so energy, rate of change of energy at any given k, some of it is being dissipated, and in fact it is proportional to how much energy it has with a k squared here. So you can imagine that larger the k, larger the dissipation, that is higher the frequency. If you want to convert wave number to frequencies, higher the frequency of fluctuations, the faster it decays. And that's not very unreasonable, because larger the oscillations, larger the gradients, and therefore viscosity will be more effective. And then there is another term here, which is the nonlinear term. Let me represent it as simply T of k, which is the spectral transfer. So spectral transfer meaning from, this is the transfer of energy to a wave number k from every other wave number in the problem. So it may look something like that. So the function of k here, E of k will largest eddies, largest wave number, largest scales, that is smallest or very small wave numbers. You remember the relation between the length and wave number. So L is equal to 2 pi over k. So when I say large lengths, it means small wave numbers. Just remember that, okay? So you'll have energy, which may be like that, let's say. There is still some of it here. I mean, it's so small, that's why you can't see it. But k squared E of k will be nothing here, very little, etc. may do that. So this is E of k, and this is k squared E of k. So I have to put in 2 nu, etc., but to get the dissipation. And this T of k may do something like that. So basically takes the energy from here and distributes it down here. So something like that, T of k. Now, what you have is, this is the dissipation at any given wave number. So if you want to get the dissipation epsilon, all you have to do is take 2 nu k squared E of k and integrate it over all wave numbers. So that would be 0 to infinity. And that's the same epsilon. You see, there are many different ways in which you can do that. This is through gradients. The square of the gradient here translates to having a k squared, and just this integral over all possible wave numbers. Usually it is concentrated in these high wave numbers, and there is very little dissipation in large scales. So you stir the flow at the scale at which you stir, nothing is being dissipated, or very little. Somehow by nonlinear interaction, it's producing smaller scales and so on. And then you have some small enough scales where viscosity can become effective, and then the energy is sort of drained out. So this is roughly the picture one has in mind. There are several implications of this relation here. I want to dwell a bit on that. Yeah.
You've drawn DFK and the diffusion term as having peaks at roughly the same place.
Oh no, I'm not sure. I know that.
So that's not.
No. This is not peaking at the same places. The same place. These two, let's say, these are not peaking at the same place. Yeah. I wrote it only qualitatively, and it depends on the Reynolds number and all that. So, Let's take one interpretation of. Oh, by the way, as I mentioned yesterday, this is called a dissipative anomaly. Anomaly um, being that there is finite dissipation even when the viscosity goes to 0. So let's take a couple of interpretations of that. So I have here du squared over dt with 3 halves and all forgotten, but it doesn't matter actually, is dissipation which is a u prime cube over L p, let's say. You can write this as um, in this form a u prime squared, yeah, let's put it that way, times another u prime over LP. Just rewriting the same thing. Or in the way I want it, u squared over LP by u prime. So this is the energy, right? If you like, I should put u prime squared too. But I don't know. Sometimes I'm messing it up. So this is the energy, and this is a time scale. So this is energy was divided by time, and of course that is the rate of energy depletion. Any rate is simply energy divided by time. Um, so you might think of it like this. Excuse me. Let's say you write like this. This is I'm writing the same thing a number of times in different ways. So this is a time characteristic of decay. So I have the energy and I have the energy decay rate. Therefore, this is characteristic time for decay. And what is this here? U prime is the mean square energy. As we saw, most of the energy is contained in low wave numbers or large scales. So this is a velocity characteristic of large scales. And this L is also a length scale characteristic of large scales. So this really is a time scale corresponding to large scales in the flow. So this tells you that is a time scale which is of the order of one large scale in the flow is almost the same except for this thing here and subject to some small interpretational issues. It's the same as the time scale for decay. So you know what it means? It means that if you shake the box or stir the flow at some length scale, more or less, and allow it to decay, if the large scale changes by a conspicuous amount, let's say by a factor 5 or something like that, by that time all the energy is depleted. So basically, the time for decay is an adjustment of the large scale somehow. So the large scale has given up its energy in some fashion, and that essentially is the entire decay process. So what this really means is that if you think of the following, which I think I'm putting thoughts in your head which are not really in the equations yet. Let's say the energy from here goes to here, and from here to here, here to here, and then it gets dissipated. There's a time of energy transfer from this scale to this scale, which is, let's say, half its size or something like that. And then to half its size yet, and half its size yet, and half its size, etc. Now, by the time this one gives up its energy to the next scale, which is, typically of this order, LP by U, because this is LP and U prime is its fluctuation. Already the whole thing has decayed. What it means is that these time steps are becoming much smaller. You see, the main time scale is this, and then this time scale will be half as small, and half as small, etc. So in a way, it's the total time, which is the sum of all of them, is more or less determined by the first step. That's the major thing. The other things are of the same order. I mean, if you sum all of the others, it may give you another one, or another number 1, 2, or something like that. So that's the key thing to remember, that the main adjustment that takes place in the decay process concerns the large scales, within which time everything else has already happened for the rest of the flow. So that's one interpretation. The other interpretation of this dissipative anomaly is that I have written here, let's take this one, and we write this as A U prime LP, and I put U prime squared or LP squared. Now, what does that imply? So this here is a typical velocity gradient at the large scale. See, because U prime is a velocity which may change over a length scale of order LP. And so this is a typical large scale gradient, gradient. And the energy dissipation, if you take the large scale gradient, it would be multiplied by some quantity, large scale gradient squared, right? That's what it is. It would be multiplied by a quantity, and this quantity is like a viscosity. If you remember, dissipation is like nu du dx squared, that kind of thing I wrote at the bottom there. So, but if I take the characteristic velocity gradient as given by the large scale, then the number sitting in front, which is like viscosity, is proportional to the product of the velocity and the length scale of the large scale. In other words, if you want to know how much energy a tornado, for instance, dissipates, tornado having a length scale and a velocity scale, you are not going to be able to compute it by saying, well, energy dissipation is nu times the velocity of the tornado divided by the length scale of tornado. Because this is really what is dissipating is not the big scales, but the small scales. And the way to do that is, instead of nu, if you replace it by some other quantity like this, which is the product of the velocity and the length, then you will be fine. You can use and this is the so-called eddy viscosity, right? This is roughly what I already told you yesterday or day before or whenever, where I said in the equations of motion, it was yesterday, if you write an equation for mean velocity, for instance, I said you will have an additional term which is equal to d by dxj of dui of ui uj bar, like that. And I said sometimes you can write it as this quantity here as nu effective times du dui dxj, let's say, dui dxj. I need a tensorial thing to make it correct, but never mind. So I said this will be an effective viscosity. So basically, you're replacing the turbulent transport by an effective viscosity times a mean velocity gradient. the idea is exactly the same. In a different way, you're replacing the viscosity that you might have had if you're taking the right gradients into account. Instead of the real viscosity, you use this thing called eddy viscosity. So eddy viscosity is like that. So let's now pause for a minute and say I have a tank which I am shaking, and this is 100 centimeters I wrote down yesterday, and this is the velocity RMS is say 10 centimeters a second. The kinematic viscosity of the fluid, if it is water, let's say nu, it's 0.01 centimeter squared per second, but the effective viscosity is a product of these two, which is 1000 centimeters squared per second. So it's already, you see, several fold 1000 times 100, 10 to the power 5 larger. So a whole lot of representation of turbulence effects is hidden in the use of this eddy viscosity. Atmospheric scientists and geophysicists in particular continue to use that, although everybody knows that it is a little tricky because it depends upon these length scales and velocity scales, which are um, characteristic of a flow, not of a fluid. And furthermore, if you have a homogeneous flow, it has only one velocity scale and one length scale, or there may be others, but that's one effective length scale for the large scales. But if you have a shear flow, for instance, there may be many different scales. For example, you have, let's say again, flow between parallel plates. The flow is correlated in this direction by a certain length scale, whereas it's correlated over a direction, over a dimension of the order of the half channel height or something like that in that direction. And it may be correlated in a different way in this direction. So whenever you have anisotropy, you certainly have anisotropy in this thing. And your epsilon, your eddy viscosity, is not going to be simply a scalar, but it will become more complicated object like a tensor. Just another remark I repeat myself here is because of this relation, the smaller the viscosity, and this is a constant, right? So smaller the viscosity, the larger the gradients have to be, and that means the energy distribution has to be moved up to smaller and smaller scales. That means larger and larger wave numbers. So in this case, if nu goes to 0, this peak just keeps moving to the right continually. It's some adjustment happening here, but it just moves further and further out. Because nu going to becoming smaller means the gradients have to become larger, and that means basically you have to have higher wave numbers. It just moves this way. So you can therefore imagine that if the Reynolds number is large enough, this peak and this peak are really quite separate from each other, as I have sort of drawn already. And that means that what is happening in the dissipative region is not being influenced by the large scale directly. It may have a direct effect if there were energy flux going like that. And the traditional thinking is that's not the way it works, although there is some part of it happening for sure. But most of it is in this way. Therefore, the energy, this part of the spectrum is no longer dependent on all these spectral characteristics here. So that will be determined by local characteristics, what is happening here locally. It's like letting your child go away into a foreign country and the child is no longer being controlled by you, and she does what she wants to do, governed by local conditions. So that's where we are on this. So now, all of this is phenomenology, right?
That these are invisible springs which go all the way
That could be, I mean, the culture strings are so many that even though you have possibilities there, you are inhibited by your background. So that may happen, yes. In fact, I will say that something like that does happen. So this is all phenomenology, but I haven't solved the equation. That equation I had written down there for EFK, or the Karman-Haworth equation to solve this F. I haven't done any of that simply because the nonlinear terms are inhibiting us. But if you make a little hypothesis, it will be possible to say a lot. And that's what we will do now. So far, what I have said is all formally correct. I mean, there is nothing I have really made approximations about. I only said this is large, it moves that way, and all that kind of thing. There's nothing wrong with any of these definitions. They are just definitions to start with. So we have put in a lot of things on the blackboard, but making very little progress. I'm just giving you one thing after another. It would be nice if I could say E of k is some function of some well-known function of wave number, If I could do that, that would be great, and we can't. And what we know is, due to Kolmograph's phenomenology, let's put it that way. I don't know. I'm sure I'm messing it up. Phenomenology, yeah. Now, the idea is so powerful that so many people came to the same conclusion around the same time. Maybe a little bit later, but around the same time. The one that followed Kolmogorov is Obukov, who was his student, and they wrote two separate papers. And in the same year, just actually papers appeared more or less side by side, if I remember. So I don't know, they must have talked to each other, and but Kolmogorov wrote it differently, and Obukov wrote differently. And then in the Western world, Heisenberg did it in Cambridge when he was a prisoner of war in Cambridge, near Cambridge. He and von Weizsäcker were thinking of physics. They didn't know what to do without any tools. So they thought of turbulence, and Heisenberg and von Weizsäcker, I think something like that. They also wrote separate papers in the same issue of the Proceedings of Royal Society, something like that. In the US, Lars Onsager did the same thing. So it's very repeated by many people, giving the same result, but essentially slight differences. And of course, Kolmogorov and Obukov works was not known to these guys, or not known to Onsager, and Onsager's work was not known to these guys. This was wartime, and everything was sort of, constrained to move one place to another. But it's still known by the name Kolmogorov, because undoubtedly he was the first one who made the proposal. So there are two preliminaries in Kolmogorov's phenomenology. And one of them, as I already stated, is epsilon is of order 1 even as nu tends to 0. I mean, Kolmogorov had absolutely no empirical data at all on this. But he somehow imagined that that's what happens. And on hindsight, it is not so bad. You would think that that might be what should happen. But I must say I am very impressed by the fact that absolutely without any data, he could do that. G.I. Taylor, before that, had actually conjectured the same. So that's one. And the second thing is the idea of local isotropy. It's not necessary for us, but it really stretches the validity of the Kolmogorov's theory if you think that is correct. So the idea is that even if on the large scale, on the global scale, the flow may be very anisotropic, when you get to smaller scales, things become more and more isotropic. Now, it's not very hard to understand. For example, if you take this situation here, this is where the energy resides. That is where you are pumping in energy, and if you pump it, but energy is there. And of course, the next scales will be affected by what you have done here. That is, how you have stirred will influence the next range of scales, but a little bit less than here. By the time you get there, it has already forgotten what has happened here to a larger degree, etc., etc. But when you get down to really small scales, which might be of interest for us to consider for dissipation and things like that, it has forgotten how it was generated. It has, on the other hand, been influenced by how the energy transfer process occurred, not by how you generated it. Okay? So in the examples we are talking about, a tank of fluid in which you are shaking and leaving on the desk, the biggest scales obviously depend upon how you shook the box, whether you did it this way or that way, all of that kind of stuff. But, or whether you stirred it like this, or you simply shook it in certain fashion different from that. But as you look at smaller and smaller scales, this memory of how you created them will just become diminishingly small. So that's the idea of, when the memory of how it was created becomes diminishingly small, here clearly, if you stir it one way, you might have one type of anisotropy, another type of anisotropy if you did it differently. But when all those features are being lost, when you get down to smaller scales, this is the concept of local isotropy. So even though on the overall, globally, you might have anisotropy, locally you would have isotropy. So in particular, what this means is that even whatever the flow, however you created the flow, this part of the spectrum would not be dependent on how you generated it. Therefore, in particular, the energy dissipation can always be defined by this, or it can always be defined by this, which is the isotropic result. So this is the isotropic result, and therefore the same isotropic result can be used for any kind of flow you like. So even in a channel flow, for instance, where it's completely anisotropic, if you use 15 nu du dx squared and average this quantity, that's a very good approximation to epsilon in such cases. And this has been measured, and probably not very well measured, but at least numerically simulated. Not very well simulated, but by and large you think that that is correct. Now, so this adds to our thinking that perhaps the way it happens is really like that, going from one step to another, or the energy cascade, as I mentioned yesterday. But not everything is well in this kingdom of local isotropy. For example, if it were isotropic, small scales were isotropic, when I take a derivative, I'm already going to small scales, right? Because I have a k multiplying that, which will push you to the large scales. If I take higher derivatives, it will push you further and further out into smaller scales. Now, let's imagine a quantity like this. I have a coordinate system, 1 here and 2 here, or y if you like, and x, and v here, u here. So if I take a quantity like dv dx cube, okay, this is already small scale because I have taken derivatives. Now, what should it be like if I had reflectional symmetry? So, reflectional symmetry is part of isotropy. Therefore, I should be able to say when x goes to minus x, that is when I am taking derivatives in that way, it should be the same, right? If I take x to minus x, I will indeed get dv dx cube with a minus sign, and the only way it is possible is if it is 0. So that implies, local isotropy implies something like that. But actually you measure this quantity, it is not 0 in other flows like boundary layers and channels and things like that. Whereas this part is true. This part is true, but this part is not. In some sense, therefore, this is an indication that more than just an energy cascade actually does occur in turbulence. There is some direct interaction between the large and small scales, and it was not clear how it would happen. I will tell you how people thought about it and tell you what is wrong with it. People, you may have seen sketches like this in very, very well-known books, and authors use this. So this kind of cascade process, which I have described in the spectral space, is thought to be following in the real space. So real space, I have these big eddies like that, which I created in some fashion, and these eddies become unstable because the Reynolds numbers are very high. Okay, this has a large velocity and a large length scale, so this will become unstable, and it will break down into smaller ones, and then it breaks down this way, and eventually you have little spheres rolling out, so to speak. So you have all these characteristics lost, and eventually this is the range somewhere here, which corresponds to this in the spectral space. So people write sketches like this, and now you can understand why, if the energy cascades proceeds this way, these eddies may not really relate directly to what happened many generations ago. Only your parents' generation probably influenced you. But if you have long history, well, that's another story. But what happens really is nothing like this at all. What happens in the turbulence is that when the breakdown process occurs, it's also related to vortex stretching, and vortex stretching means you have a little blob of vorticity, it gets stretched. That means it becomes long in one direction and short in the other direction. And of course, if you stretch it too long, it won't remain intact, it will break down. And so, but you might imagine stretching and so on and so forth. But eventually what you end up with here is not a string of little spherical objects, but very thin objects like that, vortex structures, maybe line elements, maybe sheets, maybe something in between, and things like that. And these, while in one dimension they are really very small, corresponding to what we have been discussing. In the other direction, they are not. If they are not small in the other direction, it's conceivable that their motion is in fact dependent on these large scales. You see, so they might ride over these big ones and they might still get stretched by the big ones, and therefore some influence of the large scale could be felt directly by this. And it's not surprising, because even in this phenomenology, interactions take place only through triads, as I mentioned before, triad wave numbers. So if you have a triadic interaction like that, energy from here by interacting with this is given to that. But if you have a thing like that, energy from here by interaction with that is given to that, which is a very large wave number. So directly you might have a coupling. In principle, therefore, direct interaction is possible. In practice, it is relatively small, because the probability of such interactions is much higher than the probability of such interactions. I mean, this is all empirical. I mean, there is really no theory that will tell you that local isotropies these local interactions are correct, although there are papers. For example, there's a paper by Gregory Iyenk, I forget where it was written, which tells you that in fact local interactions are what is the most dominant part of it. So these are the two preliminaries in Kolmogov's phenomenology, and now we are ready to state his hypothesis. And the hypothesis, the first hypothesis, so by the way, this is 1941, so many years ago, and for that reason, in the jargon, it is referred to as K41. Because Kolmogov came up with another hypothesis in 1962, 20 odd years later, and that's referred to as K62. So, the first hypothesis, the first hypothesis, the motion associated with large wave numbers. This is not how Kolmogov stated it, but basically this is the same thing, are small scales. Is uniquely determined by epsilon and nu. Now, what is he saying? He is saying that motion of small scales, that is scales here, are not controlled by anything corresponding to this, but is completely controlled by what is happening here. What is happening here? Energy is being dissipated, and it's being dissipated by viscous action. Therefore, those are the only two things that matter. It does not matter how you stirred it, what the length scale of stirring is, how fast you stirred, and all this kind of stuff. Well, that's the first hypothesis. So, for the following calculations I'm going to make, it's convenient for me not to say that they depend on epsilon and nu, but out of epsilon and nu, I'm going to construct a velocity and a length scale, and I'm going to say it depends on them. I mean, it's basically exactly the same thing. So I construct a length scale called eta, which is nu cube over epsilon to the power quarter. This has a dimension of a length scale. As you can see, nu has a dimension, what is it? L squared by t, and nu cube is L6 by T cube, and epsilon has the dimension L cube over no, whatever. No, wait a minute. Epsilon is U cube by L. Therefore, its dimensions are L squared over T cube. So this is L squared over T cube. T cube cancels. I have L to the power 4 here. A quarter power of that is an L. So that's the length scale. And I can also define a velocity scale, and let's say call this little v, and this is nu epsilon to the power a quarter. I think you can check that very easily. I think this is correct. Let me check. Yeah, no, that's correct. Yeah, okay. So, in other words, the motion associated with large wave numbers of small scales is uniquely determined by eta and v. If you do it like this, let's construct a Reynolds number based on this length scale and this velocity scale. So v eta by nu, and that is nu epsilon to the power quarter, and nu cube, nu 3/4 over epsilon to the power quarter times nu. Okay. So you have a nu to the power quarter, nu to the power 3/4 cancelling with this, and epsilon to the power quarter cancelling with that, and I have 1. So Reynolds number is 1. So the thought is that you have a large scale, put in at high Reynolds numbers, it is unstable because its Reynolds number is very high, breaks down yet again because its Reynolds number is high, breaks down yet again because its Reynolds number is still high, not as high as that one. And this kind of thing proceeds until you get down to such scales whose Reynolds number is 1. So a Reynolds number 1 means the inertial and viscous effects are just the same, and it doesn't have any further instability, and it will sort of, everything will die. Fluctuations will just get killed by viscosity when you're around there. Therefore, in this spectrum that I have drawn, the energy dissipation is taking place here, and this scale would correspond to eta, something like that. It's, say, 1 over eta or 2 pi over eta or something like that. Now, of course, when I say the Reynolds number is 1, everything is killed off right at that point, it doesn't exactly happen that way. It starts to happen a little bit before and continues a little bit later. But these scales are small enough that the Reynolds numbers are of odd unity. And in particular, the scale Kolmogorov, this is called the Kolmogorov scale, by the way, not very surprisingly. Kolmogorov length scale and Kolmogorov velocity scale, length and velocity. So, what you now have in a flow typically is you have a scale which is corresponding to 1 over LP or LP, where you have stirred the flow more or less, not exactly correct, but more or less. From there to there is the range of scales that you have in a flow. So the range of scales, range of length scales is L over eta. From L to eta, but that's the ratio of the scales. And what is that? Let's calculate it by using these definitions. Let's put L eta is nu cube over epsilon to the power quarter, and L, I rewrite this, nu cube, nu to the 3/4, epsilon to the power quarter I take there, But what is epsilon? Epsilon is, you know, here, a u prime cube over LP. Even if you forget a and take that to be unity, so I will have to put for epsilon u cube to the power 3/4, I mean 1/4, right? Not 3/4, and L to the power 1/4. So I have here UL over nu to the power 3/4. So this is the Reynolds number. I mean, if you want, you put P there, but if not, and this U prime. So this is RELP, if you like, to the power 3/4. Usually people don't put in this P and all that, so I could erase this. So that's the ratio, eta. So when the Reynolds number is large, like 10 to the power 8 or something like that in the atmosphere, you can imagine that these scales are very, very large. The scale ratio is very, very large. If you have 10 to the power 8, this scale range is 10 power 6. And now, if you have a three-dimensional flow, and it happens in all the other directions too, you have 10 to the power 6 times 10 power 6 times 10 power 6. That's the range of scales you would have to worry about. Now, another thing we can do is you can get the ratio of this velocity to u prime. This is the Kolmogorov velocity to the RMS, root mean square velocity. And again, use this definition, nu epsilon to the power quarter divided by u prime, and put for epsilon this quantity here. And you do that, and you will get u prime L over nu to the power minus half. So the two will change with Reynolds number, but not as fast. You can actually do a little bit more than just definitions, because I haven't so far done anything except say epsilon and nu, and I changed it to eta and v. Now let's see one consequence of this. One consequence of this is that this thing here depends only on v and eta, right? And therefore, this integral has to also depend on the same things. So let's do some simple calculation here. But before I do that, let me put. So the important consequence of this is E of k for large wave numbers would have to be of the form v squared eta phi of k eta. This is the only way you can write the spectral density that depends only on v and eta. K has the dimensions of 1 over length, so it has it normalized by eta. And what are the dimensions of epsilon? It's energy, E, energy per wave number, that is equal to energy times a length. And the only energy, you have kinetic energy, you can express it only in terms of v squared, because that's the only thing you can think of here. And this length scale is that. So that's the form in which you can write it. And that's a very important thing. So if you measure the spectrum of the turbulent energy, normalize it by Kolmogorov velocity and Kolmogorov length, it has a unique form when plotted against k eta, independent of whether you measured in the ocean, you measured in the Jupiter, or you measured in the laboratory. etc. So actually that turns out to be true, and I will tell you a little bit later on what the experimental evidence of it is. So this is the direct consequence of Kolmogov's first hypothesis. It doesn't tell you what this phi of k eta is, but it has to be of that form, and theoretically it is not possible to know what it is, but I can tell you what form it might take empirically. So empirically, E of k towards the large wave number is like k to the power alpha exponential minus c k eta, something like that, where alpha is about 3 and the c is about 7. This is all coming from numerical simulations. You simulate it towards the end, it has this kind of form. So if, maybe that's good enough. But we don't know what this phi is. But we can do a little bit, put a little constraint on phi in this expression. So we have this. So I'll write this 2 nu. I have to normalize everything by eta. So I have k eta squared, and I have to put 1 over eta squared here. And E of k eta here. And let's put for E of k, this quantity that we have, v squared eta phi of k eta. And I have dk eta, and I need to have 1 eta somewhere here. Right, so I need to do that. So some etas cancel, etc. So I will in the end have, as a result of this, the following relation, integral k eta squared 0 to infinity. By the way, you always put the limit 0 to infinity because you're taking the dissipation from all the way up to here. But we know that the dissipation here is very, very small. So even if you went 0 to some other value, it wouldn't matter. But technically, let's put it like that. So 0 to infinity k eta squared phi of k eta d of k eta, this is equal to half. That's the constraint I get, because in nu and eta I have an epsilon which will cancel, and I just have a half sitting there. So r, if you like, z squared phi of z dz equals half, and that's the only constraint on phi. Otherwise, it has no other constraint. But it's already important to know that if you normalize everything in this fashion, you will get a universal spectrum, which is this phi. Okay, but this still is not enough. It's telling you nothing about the spectrum exactly. So Kolmogorov went ahead and made a second hypothesis, and that will allow you to calculate the spectrum, and we can rest after that. So what time is it now?
It's like 5 or 7 minutes to 1.
So I can stop at 1, something like that. Okay, so let me do this one. You may go beyond that for a few minutes, but not for very long. Now, so let's take this case. For our own benefit, let the Reynolds number be very large. So what I have is, I have this thing here somehow going trailing off, and this one here like that, very far away from this peak. And I have many steps in the cascade, etc. So Kolmogorov first said for small scales, that is scales which are far away from here, everything depends upon those two quantities, epsilon and nu. But suppose I looked at these intermediate numbers, wave numbers, which are very far away from here, that I don't have to worry about LP and U and all that kind of stuff. But it is still far away from here that I don't have to worry about viscosity, because they're still large enough scales, and therefore their Reynolds numbers are high, and therefore I'll just say viscosity is irrelevant. Then what is the only thing that will matter here? These large scale properties don't matter, the viscosity doesn't matter, but what these scales do is they adjust themselves to this energy cascade. You have to maintain a certain balance in your bank account. The faster you put in, the faster you have to take out, and therefore your behavior is controlled essentially by how fast you put in, which must be how fast you take it out. And therefore, the only thing that matters in this region is this flux of energy, the energy going from here to here to here to here to here, etc. And what happens to this flux of energy? When it gets there, it gets dissipated. So you might say, therefore, the only thing that matters is epsilon, not epsilon in itself, because epsilon is the energy flux going through here, eventually vanishing, eventually manifesting there. So only thing that matters is epsilon. So what this means is this E of k, it's still, this form is still correct in this region. In this region, because this is far away from here, all of this is controlled by that. Nevertheless, there is a part of it in which only thing that should appear is epsilon, not viscosity. And how do we do that? That's very easy to do. Let's say, put them all in units we know. This is nu epsilon to the power half, and this is nu cube over epsilon to the power quarter. So collect the powers of nu. I have nu to the power half here, nu to the power 3/4 there, and that will give me nu to the power 2/4, 5/4, right? Something like that. That's what I will have. And this phi of k has to be such that its form has to kill off this power of viscosity. So this will be a power in k eta, because eta has a viscosity in it. That power is such that it will have to balance this 5/4. And the only way to do this, nothing arbitrary at all here. And what you get is, if you take this to the power 5/3, minus 5/3, k eta to the power minus 5/3, then what happens? Eta to the power minus 5/3 is nu cube by epsilon to the quarter. So I will have, I have to get this right power, but that is correct. I probably made some error, but we could do that if you want more slowly. But basically, that's the point. The point is, it will have to have a power law in such a way that the dependence on viscosity disappears. And if you do that, you will get E of k is some constant sitting in front, let's say Ck in honor of Kolmogorov, epsilon to the power 2/3, k to the power minus 5/3. Okay? I think you should sit down and do it. It's really very trivial, but I always make mistakes on the blackboard. So that's the, by not solving anything, but by making what looks like a very plausible set of hypotheses, we came to a result, which is this is a celebrated 5/3 spectrum. Everybody knows about this, so you should definitely know this. People who don't know anything else about turbulence always know this. Definitely important to know. Every physicist knows that. So you have a 5/3 result. So what it will look like is, these little things that I'm drawing, let's plot, instead of linear scale, let's plot the log scale, this thing in log scale, so you can see all of them a little bit better. So you will have logarithm of k eta here, and logarithm of e divided by v squared eta. What happens is, when k eta is very large, that is you're way out there, you will get a universal function about which we know nothing except that it's constrained by this integral relationship. And whether you take mercury, you take water, you take whatever, all of them have to have the same spectrum. And in fact, there have been dozens of measurements made, and they all follow each other more or less. And I'll qualify that in a minute. Now, this will go off like that. If the Reynolds number is higher, it will do that. And if the Reynolds number is higher yet, it will do that. And higher yet, it will do that. So this is now minus 5/3 slope. And this is increasing Reynolds number. Or whatever you want. So this is this minus 5/3 region for large enough Reynolds numbers. For small Reynolds numbers, there is no intermediate region because this peak is sort of close enough to it, then there is no intermediate region. And the larger the Reynolds number, the larger this intermediate region you get. And this region, where you have that thing is called inertial range. And this region, where most of the dissipation occurs, which would be somewhere here, these are all very loose boundaries, so you shouldn't be too taken by them. This is the dissipation region or dissipative region. Dissipative, and this would be the energy containing region. So as you see, most of the energy is contained here because most of the area under the curve is coming from just there. So the idea that energy containing scales and the dissipative scales are different is a very interesting idea. I mean, you have no connection across scales except through the energy transfer, and it enables you to calculate a whole host of things, and we can calculate a couple of them later on. But of course, you don't know whether any of this is true except by empirical evidence. And the empirical evidence, which I just a minute ago said, all of them collapse with each other, on each other. But this is a log scale, remember. And the log scale, if you have a high Reynolds number, is 7 to 10 decades here in energy. And then you're looking at universality on a log plot. You can always be fooled into thinking that everything collapses on each other. A factor 2 would make no difference at all on this, right? Because on a plot which is that size on the A4 paper, and you have all this data plotted, and factor 2 difference, factor 3 difference doesn't show. And therefore, it's conceivable that there is a little problem with it. Likewise, it is conceivable that this minus 5/3 slope on a log-log plot, getting a power law exponent is not very easy. If you are a practitioner, you would know. To get this slope to 1 decimal place, you need at least 1 decade here. And that means the Reynolds number has to be a certain value. If you want to get it even closer to 2 decimal places, as a matter of empirical practice, you need 2 decades. And 2 decades and 3 decades. Now, if you go to geophysical flows, like ocean, for instance, you can get maybe 2 or 3 decades, but not otherwise, generally. And making measurements in the ocean is very hard, in part because the large scales are no longer steady. You have to average over a long period of time, and the ocean is not the same this morning as it is this afternoon. So you can only make measurements for a limited range, and that puts a lot of constraints on various things. That's why having a laboratory experiment at very high Reynolds numbers, which you have complete control on, is very important. That's why these cryogenic experiments I mentioned earlier can become very important. The only problem is, of course, the resolution is going to be harder and harder in demand, and there again you have a problem. So there are issues related to that. But by and large, if you look at it from a distance and not go too close to it, this looks like a very reasonable description of what happens. If you get very close, then many other things probably become important, and we will discuss that in maybe this afternoon. Okay.